Welcome to today's session. We're diving into LeetCode problem number 808, titled Soup Servings. This problem challenges us to analyze probabilities in a unique way, combining recursion, dynamic programming, and mathematical intuition. Let's explore the problem, break it down, and develop a solution together. In this problem, we are working with two types of soup, soup A and soup B. Initially, we start with n milliliters of each type. The goal is to serve these soups using one of four possible operations, which are chosen randomly with equal probability. The operations allow us to serve 100 milliliters of soup A and 0 milliliters of soup B, or 75 milliliters of soup A and 25 milliliters of soup B, or 50 milliliters of each, or finally, 25 milliliters of soup A and 75 milliliters of soup B. Serving continues until either soup A or soup B runs out. Once one type of soup is depleted, no further operations can be performed. Our task is to compute the probability that soup A runs out first, plus half the probability that both soups run out simultaneously. The result should be returned as a floating point number rounded to 5 decimal places. Additionally, for any value of n greater than or equal to 4800, the probability can be directly returned as 1.0, since soup A is almost guaranteed to run out first under such conditions. Let's look at an example to better understand the problem. Suppose n is 50. This means we start with 50 milliliters of soup A and 50 milliliters of soup B. There are four possible serving operations. We can serve 100 milliliters of soup A and 0 milliliters of soup B, or 75 milliliters of soup A and 25 milliliters of soup B, or 50 milliliters of each soup, or finally, 25 milliliters of soup A and 75 milliliters of soup B. For these serving combinations, we calculate the probability that soup A runs out first, or both soups run out simultaneously. After considering all possible serving scenarios and their probabilities, the result is determined to be 0.62500. Now let's examine another example where n is 100. Here, we begin with 100 milliliters each of soup A and soup B. Again, the four serving operations are applied randomly with equal probability. Using these operations, we calculate the probability of soup A running out first or both soups running out simultaneously. The result in this case is 0.71875. This showcases how the initial amount of soup affects the probability when we account for the randomness of the serving operations. The problem also comes with a few constraints and additional points to consider. First, n is a non-negative integer and can range from 0 to 10,000. The solution must be accurate within a margin of 10⁻⁵ from the actual answer. If the initial soup volume n is 4800 or greater, the result can be directly returned as 1.0 because, at such large quantities, soup A is almost certain to run out first due to the law of large numbers. To handle this problem efficiently, especially for larger values of n, techniques like dynamic programming or memoization are often used. These methods optimize the computation by avoiding redundant calculations, ensuring that the solution is both accurate and efficient. To tackle the soup servings problem, we first consider a brute force approach. The idea here is to explore all possible sequences of serving operations. Each serving operation reduces the quantities of soups A and B by fixed amounts, and the process stops when either soup A or soup B, or both, are completely finished. This can be implemented using a recursive function that branches into four paths for each serving operation. At every step, the function calculates the probabilities based on the remaining quantities of the two soups. However, this approach comes with a significant drawback: the number of recursive calls grows exponentially as each call branches into four new paths. For large values of n, this results in excessive computational costs and timeouts, making the brute force method infeasible. To address this, we can shift to dynamic programming with memoization. The key insight here is that the brute force approach repeatedly computes probabilities for the same states. By storing these intermediate results, we can avoid redundant calculations and improve efficiency. This method takes advantage of the overlapping subproblems inherent in the serving process. Additionally, for very large values of n, the probabilities tend to stabilize, allowing us to approximate the result effectively. The dynamic programming implementation involves a recursive function with memoization, where we calculate probabilities based on the current quantities of soups A and B and define base cases for when one or both soups are empty. This significantly reduces computation time compared to brute force while maintaining accuracy for moderate values of n. The dynamic programming approach is built upon a set of well-defined base cases. If soup A is empty while soup B still has some quantity remaining, the probability of soup A finishing first is 1. On the other hand, if both soups are empty simultaneously, the result is 0.5, indicating equal likelihood of both finishing at the same time. If soup B is empty while soup A still has quantity remaining, the probability is 0, as soup B finishes first in this case. Using these base cases, the transition involves calculating the probabilities for any state, A, B, by considering all 4 possible serving operations, each with an equal probability of 25%. This reduces redundant computations and ensures that probabilities are efficiently reused. The computational complexity of this approach is approximately n squared, where n represents the scaled soup quantity. While this is significantly better than the exponential complexity of brute force, it still poses challenges for very large values of n. To further optimize, we introduce scaling. The intuition here is that for large n, the probabilities stabilize and converge to consistent values. By scaling down the soup quantities, we can reduce the problem size without compromising accuracy. This involves dividing n by the largest serving size, which is 25 milliliters, and rounding up. The same memoized dynamic programming approach is then applied to this reduced state space, making the computation far more manageable. This optimization significantly decreases runtime, as the state space becomes much smaller, and the computational complexity is lowered accordingly. Among the approaches considered, the optimized dynamic programming method with scaling emerges as the most effective strategy. The brute force approach, while conceptually straightforward, is computationally prohibitive due to its exponential growth in complexity. Memoization addresses this by reducing redundant calculations and improving efficiency for moderate values of n. However, even memoization struggles with very large inputs because of the sheer size of the state space. Scaling provides the perfect solution for this scenario by leveraging the observation that probabilities stabilize for large n. By reducing the state space through scaling, we achieve a balance between computational efficiency and result precision. The trade-offs of this scaling approach are minimal. Although it introduces a small approximation error, the gain in efficiency is significant. For smaller values of n, the unscaled dynamic programming method may be simpler to implement, but for larger n, scaling is indispensable. By comparing complexities, we see that brute force is exponential, unscaled memoization is n squared, and scaled dynamic programming reduces this to open parenthesis n divided by 25 close parenthesis squared. This makes the optimized approach the clear choice for handling large inputs, as it achieves efficiency without sacrificing meaningful accuracy. Several key observations form the foundation of this optimized approach. First, the stabilization of probabilities as n grows large allows for the scaling technique, significantly reducing the state space. Second, dynamic programming efficiently avoids redundant computations, while memoization ensures that intermediate results are reused rather than recalculated. Finally, scaling the soup quantities by the largest serving size, 25 milliliters, is the critical insight that enables the solution to handle large inputs without losing precision. This combination of techniques allows us to compute the probabilities efficiently and accurately, even for very large values of n. By reducing the problem size while maintaining the integrity of the results, this approach strikes an ideal balance between computational feasibility and precision, solving the problem effectively in a way that simpler methods like brute force or unscaled dynamic programming cannot achieve. In this problem, we are tasked with calculating the probability that soup A will finish before soup B, or that both soups finish simultaneously. The serving process involves probabilistic operations, where each operation serves a specific amount of soup from A and B. There are 4 possible serving options: 100 milliliters of A and 0 milliliters of B, 75 milliliters of A and 25 milliliters of B, 50 milliliters of each, or 25 milliliters of A and 75 milliliters of B. Each operation occurs with an equal probability of 0.25. The process stops as soon as either soup A or soup B is depleted, or both run out at the same time. To solve this, we use a brute force recursive approach that explores all possible serving sequences. First, we define the problem mathematically, representing the soup's initial amounts as A and B. Then, we recursively calculate the probability of A finishing before B by considering all possible serving operations at each step. To implement this approach, we define a recursive function, P, A, B, which calculates the probability that soup A finishes first, given the remaining amounts of A and B. The function has three base cases. If A is depleted while B still has soup left, we return 1 because A finishes first. If B is depleted while A still has soup left, we return 0 because B finishes first. If both A and B are depleted simultaneously, we return 0.5, as both finish together. For other cases, we transition recursively by computing the probability of the current state as the average of the probabilities of the four possible next states. This can be expressed mathematically as P, A, B equals 0.25 times the sum of probabilities for serving 100 milliliters of A, 75 milliliters of A and 25 milliliters of B, 50 milliliters of each, and 25 milliliters of A and 75 milliliters of B. To optimize this brute force calculation, we use memoization to store results of previously computed states, avoiding redundant computations. Finally, we initialize the computation by calling the recursive function with the initial amounts of soup A and soup B. Now, let's consider some key insights and optimizations for this algorithm. Without memoization, the recursive approach would explore all possible serving sequences, leading to exponential growth in the number of states and a high computational cost. By introducing memoization, we reduce the time complexity to O, n squared, where n represents the initial amount of soup scaled by the smallest serving size. This optimization ensures that each state is only computed once, significantly improving efficiency. Additionally, the problem exhibits symmetry. When A and B start with the same amount, the probabilities for certain states mirror each other, which can further simplify calculations. To implement memoization, we use a dictionary or hash map to store computed probabilities for each state, A, B. The function's recursive calls are managed using the system stack, so care must be taken to avoid exceeding the recursion depth when A and B are large. Finally, we must account for edge cases, such as when the initial amounts are smaller than the largest serving size, or when the inputs are very large, ensuring that the algorithm handles these scenarios correctly and efficiently. Let's look at a step-by-step example to understand how the algorithm works. Suppose the initial amounts of soup A and soup B are both 50. To calculate P, 50, 50, we compute the average probability of the following for recursive calls P, minus 50, 50, which falls into the base case where A finishes first, P, minus 25, 25, another base case where A finishes first, P, 0, 0, a base case where both soups finish simultaneously, and P, 25, minus 25, a base case where B finishes first. Once these probabilities are calculated, the result for P, 50, 50, is stored in the memoization dictionary to avoid redundant calculations if this state is encountered again. This ensures that the algorithm is both efficient and accurate. By following this process, the algorithm systematically computes the probability for any given amounts of soup A and soup B. The pseudocode provided here illustrates this process step by step, with a base case check, a memoization lookup, and recursive calls to calculate the probability for the current state. The final step in the algorithm is to initialize the computation. We define an empty memoization dictionary to store probabilities for each state. Then, we call the recursive function P with the initial amounts of soup A and soup B to compute the result. The overall time complexity of the algorithm is O, n squared, where n is the maximum amount of soup scaled by the smallest serving size, since memoization ensures that each state is computed only once. The space complexity is also O, n squared, to store the memoization data. This approach efficiently solves the problem by balancing recursion with memoization, ensuring that we explore the probabilistic serving process without redundant calculations. By applying these principles, we can accurately determine the probability that soup A finishes before soup B, or both finish simultaneously, for any given initial amounts of A and B. The solution to the soup servings problem is implemented using dynamic programming with memoization to optimize recursive calculations. First, we handle a special case where the input n is greater than 4,800. For large values of n, the probability approaches 1.0 due to diminishing probabilities of soup B finishing first. This optimization avoids unnecessary computation for large inputs. Next, the input n is scaled down by dividing it by 25 and rounding up. This simplifies the problem by reducing the granularity of serving sizes. For each state, A, B, where A and B represent the remaining portions of soup A and B, we recursively calculate the probability using predefined serving operations. These operations determine how much soup is served from each type in one step, and their probabilities are evenly distributed, 0.25 each. The helper function DFS, A, B, implements the recursive logic. Memoization is used to store the results of previously computed states, preventing redundant calculations and improving efficiency. Base cases handle scenarios where one or both soups are depleted. If soup A runs out first, the probability is 1.0. If both soups run out simultaneously, the probability is 0.5. If soup B runs out first, the probability is 0.0. Finally, the function returns the computed probability for the initial state, n, using the recursive helper. This approach ensures accurate and efficient computation for all possible serving scenarios. Here, we start with the Java implementation of the solution. The method soup servings takes an integer n, which represents the total amount of soup in milliliters. Since for very large values of n, the probability approaches 1, we add a base case to directly return 1.0 if n exceeds 4800. This optimization avoids unnecessary computation for very large inputs. Next, we scale down n by dividing it by 25 and rounding it up to the nearest integer. This is because each operation reduces the soup by fixed amounts, which are multiples of 25. By normalizing n in this way, we simplify the problem into a smaller, more manageable scale. We then create a hash map called memo to store previously computed probabilities, enabling memoization for faster recursive calculations. Finally, we invoke the helper method DFS, passing in the normalized values of n for both soups and the memo map. The helper method is designed to recursively calculate the probability for each state of the soup quantities. The DFS method is where the core logic resides. It begins by generating a unique key for the current state, using the quantities of soup A and B. If the result for this state has already been computed and is present in the memo map, we simply return the stored value, avoiding redundant calculations. Next, we handle the base cases. If soup A is empty and soup B still has some left, the probability of serving all soup A first is 1.0. If both soups are empty simultaneously, we return 0.5, as the problem specifies that in this case, we consider it a tie. If soup B is empty but soup A still has some left, the probability is 0.0. After handling these base cases, we calculate the probability for the current state by considering all four possible operations, each with an equal probability of 0.25. For each operation, we recursively call DFS with updated soup quantities, reducing the amounts accordingly. The results are summed up and multiplied by 0.25 to reflect the weighted average. Finally, we store the computed probability for the current state in the memo map and return it, ensuring that future calls for the same state can reuse this result. To solve the soup servings problem, we are tasked with calculating the probability that soup A finishes first or both soups finish at the same time. The process involves serving soups A and B according to four predefined operations. Each operation reduces the quantities of A and B in different ways, and we need to simulate this repeatedly to determine the probability outcomes. For example, when n equals 50, we normalize it by dividing n by 25 and rounding up, which gives us n equals 2. This scaling step helps simplify the problem without altering the results. We then use a dynamic programming approach with a memoization dictionary to store intermediate results, allowing us to avoid redundant calculations. Starting with the state 2, we recursively call a function, DFS, to explore all possible outcomes. The base cases ensure that the recursion stops when either soup A or B runs out, or both are depleted simultaneously. For the first set of recursive calls, we calculate results like DFS -2, and DFS -1, which hit the base condition where soup A is empty but B is not, returning a probability of 1.0 for these cases. Similarly, other calls are evaluated, and their results are combined to compute the overall probability for this state. In the next step, we continue evaluating the serving options for the state 2. For instance, the call DFS 0 results in a base case where both soups are empty simultaneously, returning a probability of 0.5. Meanwhile, the call dfs 1 minus 1 hits the base case where soup B is empty first, returning 0.0. Once we have the results for all 4 serving options, we compute the probability for the state 2, 2. This is done by adding up the results, weighted equally by 0.25 for each option, as each operation is equally likely. Specifically, we calculate 0.25 times the sum of the results, 1.0, 1.0, 0.5, and 0.0, which gives us a total probability of 0.625. This value is stored in the memo dictionary for future reference, ensuring that if we encounter the state 2, 2 again, we can reuse the result without recomputing it. The final output for this example, when n equals 50, is therefore 0.625, which represents the probability of soup A finishing first or both soups finishing at the same time. Similarly, for the next example, where n is set to 100, normalization scales it down to 4, and we initialize the memo dictionary again to start the recursive process. To compute the probability for n equals 100, we start with the state 4, 4, and recursively explore all possible outcomes for the 4 serving operations. For example, the call dfs 0, 4 results in a base case where soup A is empty but B is not, returning a probability of 1.0. The call dfs 1, 3 requires further computation, as does dfs 3, 1. Additionally, the call dfs 2, 2 has already been computed in an earlier step, so we simply reuse the memoized value of 0.625. With these results, we calculate the total probability for the state 4, 4 by adding up the contributions from all 4 operations, weighted equally by 0.25. Specifically, the result is 0.25 times the sum of 1.0, the results of dfs 1, 3, and dfs 3, 1, and the memoized value 0.625. This process continues recursively, breaking down each state into smaller subproblems until all probabilities are resolved. After completing all computations, the final output for n equals 100 is approximately 0.71875, representing the probability of soup A finishing first or both soups finishing simultaneously. For very large values of n, like 5000, however, we can directly return 1.0 due to the problem constraints. This solution is built on several key insights. First, scaling down n by dividing it by 25 simplifies the problem without altering the final result. This optimization reduces the size of the input and allows us to focus on smaller, more manageable states. Second, dynamic programming is at the core of this approach, where we use a memo dictionary to store results for overlapping subproblems. This avoids redundant computations and significantly improves efficiency. Third, the base cases ensure that the recursion terminates appropriately based on the rules of the problem, such as when one or both soups run out. Finally, the solution leverages a key property for large values of n. When n exceeds 4800, the probability of soup A finishing first or both soups finishing simultaneously approaches 1.0. By combining recursion, memoization, and intelligent optimizations, this approach efficiently computes the desired probabilities while maintaining clarity and scalability, making it well-suited for both small and large values of n. To analyze the time complexity of our solution, we start by recognizing that the input n is scaled down. Instead of working with the original value of n, we divide it by 25 and round it up to the nearest integer. This means that our problem size is effectively reduced, and we now work with a scaled input n equals ceil, n/25. From there, the recursive function dfs a b operates by considering 4 possible transitions, reducing a b by 4, 0, 3, 1, 2, 2, and 1, 3. Each recursive call depends on these 4 subproblems, giving us a recurrence relation of t, n, equals 4 * t, n 1. However, thanks to memoization, we ensure that each unique pair, a, b, is computed only once. The recursion terminates when either a or b reaches 0, so the total number of unique states is proportional to all possible a, b pairs where 0 equals a, b equals n. This results in approximately n squared unique states, which forms the basis of our time complexity analysis. Now, let's build on this analysis. Since each state involves a constant amount of work to compute the sum of 4 recursive calls, the total time complexity is determined by the number of unique states. With approximately n squared states, the overall time complexity is n squared, where n equals ceil, n/25. Shifting focus to space complexity, the memoization table stores results for all these unique A, B states. Since there are O n squared states, the space required for memoization is also O n squared. Additionally, the recursive stack contributes to the space usage. The depth of the recursion is bounded by the maximum number of recursive calls in one path, which is proportional to n. Therefore, the recursive stack adds another O n to the space complexity. When combining both contributions, the total space complexity remains O n squared. Interestingly, for the best-case scenario where n greater than 4800, the function directly returns 1.0 without any recursion or memoization. In this case, both time and space complexities drop to O(1), as no significant computations or memory allocations are performed. In contrast, the worst-case scenario arises when n is small, and the recursion explores all possible states. Even in this case, memoization ensures that each state is computed only once, so the time complexity remains O n squared. To highlight the efficiency of this approach, let's compare it to a naive solution. A naive recursive implementation would compute all possible sequences exhaustively, without using memoization. This means that each state, A, B, would be recomputed multiple times, causing the number of recursive calls to grow exponentially. The time complexity in this case would be O, 4 to the power of n, where n is the scaled input size. Memoization eliminates this redundancy, reducing the time complexity from exponential to polynomial, specifically O n squared. This optimization is key to making the solution practical for larger inputs. Mathematically, the O n squared complexity is justified because memoization ensures that each A, B pair is computed exactly once. With each state requiring constant work to some 4 recursive calls, the total work done is proportional to the number of states, which is O n squared. In conclusion, the time and space complexities of this solution are both O n squared. This efficient use of memoization ensures that we avoid redundant computations and handle the problem within polynomial time and space. By reducing the input size and carefully managing the recursive process, the solution achieves a significant improvement over naive methods, making it well suited for this type of problem. When solving this problem, there are some common pitfalls to watch out for. First, overlooking base cases in recursion can lead to incorrect results or even infinite recursion. For example, if you forget to handle the scenario where both sup A and sup B run out simultaneously, your solution might fail. To address this, make sure to clearly define and handle all stopping conditions in your recursive function. Next, a brute force approach, while intuitive, can be extremely inefficient due to overlapping subproblems. This often results in a time limit exceeded error, especially as the input size grows. To avoid this, you should use memoization or dynamic programming to store and reuse results for previously computed states. Another common issue involves floating point precision. When working with probabilities or fractions, small precision errors can accumulate, causing incorrect comparisons or results. A good practice is to use a small epsilon value for comparisons or scale your values to integers where possible. Finally, improper state representation in your dynamic programming solution can be problematic. If the states don't account for both sup A and sup B quantities, your solution may fail to capture the necessary interactions. Always ensure that your DP table fully represents the problem's requirements. Another frequent mistake is assuming symmetry without verifying it. While it might seem that swapping sup A and B would yield the same result, this isn't always the case. It's critical to carefully analyze the problem constraints to confirm symmetry before simplifying your solution. Now, let's talk about some key insights for interviews. This problem is a classic example of recursive probability with overlapping subproblems. Recognizing this pattern early is crucial, as it immediately hints at the use of memoization or dynamic programming. Additionally, this type of problem often involves decision trees, where you evaluate all possible outcomes. Efficiently solving such problems requires either recursion with memoization or an iterative DP approach. For edge cases, it's important to explicitly discuss scenarios like when one of the sups runs out or when both run out simultaneously. These edge cases often reveal whether your solution is robust. Lastly, interviewers may challenge you to justify your choice of approach, whether you used memoization, iterative DP, or even brute force. Be prepared to discuss the time and space trade-offs of your solution. This problem also shares similarities with other well-known challenges, which can help you draw connections. For instance, LeetCode 62, Unique Paths, involves a grid-based DP solution that explores recursive paths with memoization. Similarly, LeetCode 688, Night Probability in Chessboard, is another probability problem where outcomes are computed using dynamic programming. LeetCode 935, Night Dialer, focuses on recursive state representation and memoization, making it another excellent parallel. Lastly, LeetCode 377, Combination Sum 4, delves into combinations and recursive state breakdowns, which is conceptually similar to this problem. Beyond related problems, you can explore alternative approaches to reinforce your understanding. Brute force, for example, involves recursively exploring all combinations of serving sizes. While this approach is straightforward, it's computationally expensive and impractical for larger inputs due to exponential time complexity. A more efficient strategy is dynamic programming. Using a top-down approach with memoization allows you to avoid redundant computations by storing intermediate results. Alternatively, the bottom-up DP approach involves iteratively computing results for all states, starting with the smallest cases and building up. While bottom-up avoids the overhead of recursion, it can be trickier to implement correctly. When choosing between top-down and bottom-up approaches, there are trade-offs to consider. Top-down is often easier to implement and debug, especially if you're already familiar with recursion. However, bottom-up can sometimes be more space-efficient, particularly when you optimize by storing only the necessary states. Another important trade-off is precision versus speed. If you're encountering floating-point precision errors, you might consider scaling probabilities to integers. While this can help ensure accuracy, it may increase computation time slightly. Balancing these factors is key to arriving at an efficient and reliable solution. Great job! We've covered the soup servings problem, examined its unique challenges, and developed an efficient solution. Remember, practice makes perfect with dynamic programming. Thank you for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!